the analysis at county level. So both average yield and variability are reported to identify which counties show higher productivity and which show a greater inconsistency. So figure 1 shows us that variability is going to be a time problem, whereas for figure 2 is going to show us that it is also a space problem. So together they justify a framework that handles both temporal and spatial dimensions, which is exactly what our two-tier model does. So our model is built on 2 algorithms, but first, what is an ensemble learning model? So ensemble learning is a machine learning approach that combines multiple models and methods to boost predictive performance. So we can see our little decision trees. They're in a sense kind of like flowcharts or a flow with our nodes and branches. So our first model is going to be gradient boosting. So these build decision trees sequentially. Each new tree corrects the errors of the previous one. And then next we have our random forest models, which builds these trees in parallel and then averages out their results. So both of these models outperform traditional regression by learning nonlinear patterns from data rather than just assuming fixed relationships. So this study uses a 2-tier architecture that's designed to balance prediction accuracy and deployment flexibility. So tier 1 is going to be our gradient boosting combined model, where it's trained on all fields with both crops together, which results in an R² of 0.98. So this is going to be our primary model for fixed crop prediction and for generating our interpretable feature explanations. Whereas we're going to have our tier 2, which is going to be our crop-specific random forest models. So when a crop is known, then the model then routes it to the appropriate random forest model, whether that be corn or soybean. So all of the metrics are validated using a group k-fold cross-validation by field, ensuring the model was always tested on fields it has never seen before. So now let's look at how these numbers hold up against actual observed fields. So figure 3 gives us 2 ways to evaluate how well our model performed. So the left chart compares our 3 models. We have our combined gradient boosting model, which lays at an R² of 0.98, which is significantly above our crop-specific RF models. Chart 2 shows us what this would look like in practice. So the x-axis is what actually happened on the field, whereas our y-axis is what the model predicted. So both crops tracked tightly around the dotted line across our full yield range. So in practical terms, this model can help you gauge if a field, for example, will yield 145 bushels an acre of corn, and it will typically be plus or minus that. So this margin is actionable for input planning, harvest scheduling, or even market decisions. So now we can look at which variables are actually driving these predictions. So when we shift from a combined model to a crop-specific model deployment, with crop type no longer being considered, we can see that the feature rankings are shift entirely. So for corn, we have JJA precipitation, so June, July, August precipitation jumps to our top driver at 0.29, with then season precipitation and then county falling right behind. For soybean, we have the same thing with JJA precipitation, which dominates even more strongly at 0.41. So this confirms that for soybean and corn fields, on Eastern Shore, we can see that summer rainfall will be our primary force, which helps us separate our high yield years from our low ones. For soybean, it's not just weather sensitive, it's significantly more sensitive to corn, and that difference in vulnerability is one of our most actionable findings in this study. Figure 7 shows us our permutation importance. This shows us which variables actually drive prediction, measured by how much accuracy drops when each feature is being removed. So our top 4 features do almost all of the work, with everything below that reads 0, indicating that removing them changes absolutely nothing at the combined model level. So seeding rate will lead because it acts as a proxy for our crop type, but once that's removed as our feature, weather takes over as our dominant force. Figure 8 answers the question farmers and extension agents care about most, which is not just which features matter, but by how much. So each bar is our average yield shift in bushels per acre when that feature is scrambled. So the bigger the bar, the more impact that feature has on yield. So once we separate the crops, the picture shifts entirely, again with JJA precipitation becoming our top driver for both crops. Seeding rate ends up dropping down to 0. So within a single crop, it is weather that makes or breaks the season on the Eastern Shore. And also to point out, the nitrogen rate contributes meaningfully for corn, but nearly 0 for soybean, since soybean fixes its own nitrogen. The model found that independently from the data. Next, we have our figure 9, which shows how each variable moves yield while holding everything else constant. So we have our orange dash as corn with our green dash as soybean. So we can see that for corn, it benefits most from our intermediate maturity ratings, which matches the Eastern Shore's growing season. Whereas for nitrogen, it shows a yield penalty below 50 pounds per acre with diminishing returns above 160, and soybean is going to be flat throughout. Then we have JJA precipitation, which shows yield that's going to be above 20 inches, which is most critically going to be for soybean, confirming again that soybean is highly sensitive to weather. So these thresholds are directly actionable for on-farm decisions. So our figure 10 ends up showing us how prediction error falls as more trees are being added to the model. So it starts near at 52 bushels an acre and then drops steeply through the first 75 trees, then flattens out around 200 to 250. So anything beyond that buys almost no additional accuracy. So we found out that stopping early reduces computation by 40% with no meaningful accuracy loss, making this practical for real-time field-level use during planting season and not just a research tool. Figure 11 here is going to show our temporal stability and our geographic variation. So temporal stability just refers to how consistently the model performs across different years. So a model with good temporal stability doesn't suddenly fall apart in certain years. Its accuracy holds steady over time. Whereas for soybean, we can see it's a little bit more unstable, which is consistent with everything that the study has showed about soybean so far and how weather sensitive it is. Then we have our geographic variation, refers to how consistently the model performs across counties. So county level MAE ranges from 5 bushels an acre in Caroline County, for example, to then 6.9 bushels an acre in Kent County. So Caroline is going to be the most predictable because its soil and management conditions are going to be relatively the same. Whereas for Kent County, we can see that it has a higher error because it spans on a wider range of soil series across its landscape, making it inherently harder to predict consistently.